We will now evaluate this limit, and again we will not resort or refer to L'Hopital's rule. This is very similar to a limit we've previously evaluated in a previous video. The only difference is that we have a squared term here. In the previous video we only had an n without a squared. And again we are given a constant a, which is a positive number less than 1. And again, this would have been an easy limit if a were greater than 1. Because if a is greater than 1, then the limit as n approaches infinity of a to the n is just infinity. And the limit as n approaches infinity of n squared is also just infinity. And therefore, the limit as n approaches infinity of the product would also be infinity. However, what we have here is a value of a that is less than 1. And so, because a is less than 1 and greater than 0, then the limit as n approaches infinity of a to the n is equal to 0. And because this limit of n squared remains infinity, then we are left with an indeterminate limit. Indeterminate means that we cannot determine the limit. We need to do something else to actually find the limit. And here what we will do is similar to what we've done in the previous videos. So first, let's just write it again. The first step would be to guess the limit. Again, my guess here would be that L equals 0. And the reason for that is very much similar to how I've reasoned in the previous video. Here we have n factors of a to the n. And a is less than 1. And so if you have n factors of those, then you get a number that is very close to 0. And the more the value of n is, the closer it gets to 0. However, we only have 2 factors of n squared. And so you have 2 factors of n squared, and you have n factors of a. And it is rather intuitive to think that the a to the n will overpower your n squared. And so that's why the guess is that L equals 0. And to show that this guess is correct is we have to find an easier and larger sequence to work with. By easier, we mean that the limit is easier to evaluate. And larger, we mean that the value of the new sequence must be larger than these. So we have a larger here, larger values. So this is what we're looking for. And lastly, when we've found those values, we will show that the limit of the new sequence is 0. And again, this works because if the limit of the larger sequence is 0, and we know that this is less than or equal to 0, and therefore this must be 0 if this is positive, if this is rather non-negative. And we will show that in the following. So again, I'd like to write it down again. And we've said in the past that the way we can find a larger sequence is in one of 2 ways. We can either increase the numerator, or we can decrease the denominator. By doing either of these, we are increasing the value of the new sequence compared to this old sequence. And here we will choose the latter one. We will choose decreasing the denominator. And so the first step is to actually give a denominator here. And we do that by actually redefining a new number b, and we say that that is the reciprocal of a. We define it to be the reciprocal of a, and we know that b must be greater than 1 because a is less than 1. So we know that b is greater than 1. And so now we can write the limit in terms of b. And now this is our denominator, and we want to make this smaller, right? We want to decrease the value of the denominator. And the way we do that, as we've done in the past, is to express it in terms of its binomial expansion. And then we select just one term of the binomial expansion instead of all of the terms of the binomial expansion. And so the first step is to define a new number c, a positive number c, such that c plus 1 is equal to b. And we can do that because we know that b is greater than 1. And so we can decompose it into 1 and a positive number c. So this is always possible if b is greater than 1. And so we can write the limit in terms of c as well. Now it becomes n squared over 1 plus c raised to the n. And now this limit here is in a very convenient form for us, because now we can say that we can just select one term from the binomial expansion of this denominator. So I'm going to choose the fourth term, which is b cubed over 3 factorial, c cubed, and n times n minus 1, n minus 2. Again, this is just the fourth term of this expansion. And because we are only using one term instead of all the terms here, this expansion has many terms, and one of those terms is this. And so we're only using one of those terms, and therefore this value here is less than the values and than the entire sum of this. And so by doing that, we've made a sequence that is larger than this sequence. And probably you've already noticed how I'm choosing which term I'm going to put in the denominator, because we could have chosen any term, but the term that will help us decide of the limit easier is the term with one more degree of n. That means one more n than we have in the numerator. So here we have 2 as the exponent of our numerator, so we have to find the term with 3 n's in the denominator. And so we use the fourth term here. And if we just rearrange that a little bit, just bring up the constants, which is 6 over b cubed, and then I'm going to bring down the n squared. So rather, this is not b cubed but c cubed, so we've already written c cubed here. This should be c cubed. And so if I'm going to bring down the n squared, be n over n, then 1 minus 1 over n, then n minus 2. And we know that this is just a constant. This one is just 1. And this one, this goes to 0, right? And so this whole term, 1 minus 0, just is 1. And this one, we know that this goes to infinity, right? This one goes to infinity. And so we are left with limit 0, right? So we've now shown that L must be. So let's just write that again. This is what we're looking for. And we have shown that it must be less than or equal to 0. But we know that L is non-negative, right? So we already know that L is non-negative, which means L must be greater than or equal to 0. That means non-negative. And from here we know that L must be less than or equal to 0. And the only value of L that has this property is L equals 0. And so we are forced to conclude that in fact L is equal to 0.